Nadine. Hi, Gavin. They're seeing fairly focused. In the back of their homework spirals, workspace. In the back of their homework spirals, workspace. Working on the following. Like a quiz on your own, we'll grade it in a second.
So I need help I'm sorry. Bye.
Don't ask. I don't know. It's that time to like read it all down, take the key information, right? Or you can make it smaller. Maybe, maybe not. See, it just has fun, it starts bouncing. Oh, you cannot. Bounces. Sounds like a ball.
He wants
John is so sarcastically entertaining. Okay. The answers to the multiple choice are right back there. I'm going to play with the FRQ as you guys check.
She's high fiving me, I got those right. Oh my gosh. You're a high fiving me, I got those right.
Good job.
Thank you. I deserve it.
cosine's even, but what about that denominator that flipped all the sign?
Oh, yeah, well,
That made the entire thing opposite. Opposite. Did anybody already think through the horizontal asymptotes when they were doing the range for A? No? So as you go to infinity, doesn't the bottom win technically? I mean, we could do the squeeze theorem and show mathematically why it wins, but the bottom wins, therefore. The limit is 0. I have a horizontal asymptote at 0. Now a function can actually cross its horizontal asymptote, so I checked when would this be 0? Problem is it would be 0 at
0.
Oh wait, no, cosine. It would be 0 at pi over 2. Right? It's not 0 at 0. It's 0 at pi over 2 and at 3 pi over 2 because it's when cosine hits. Never mind. Range is all real numbers. Just kidding. It goes forever high, forever low because it passes through 0. It has a horizontal asymptote at 0, but even though it has a horizontal asymptote at 0, it can actually, the y's can equal 0 at pi over 2 and 3 pi over 2. 5 pi over 2, 7 pi over 2, 9 pi over 2, etc., etc., etc. What do you name that movie?
What's wrong?
Squeeze theorem to justify your answer, 2 part C. Oh, no big deal, because since cosine of x is in between negative 1 to 1, I can go ahead and say that cosine of x all over x is going to be within negative 1 over x and positive 1 over x. As x approaches, where am I going, infinity? So the limit of this one is 0, the limit of that one is 0, then therefore this one's going to get squeezed in between because he's within both of those functions. Something like that. It's not gorgeous, it's not pretty, but it's the idea. Now we have the CalcBC group chat, right? Oh. Why do we need a CalcBC group chat? Because what am I about to have you guys do? Take a picture of the multiple choice solutions and email them, text them in the group chat to Dean and Gavin, because how else are they going to check?
I don't even know if Gavin has a Snapchat.
Yeah, it's an Instagram.
Snapchat? Oh, yeah, we do everything on Snapchat these days. So what about the old school just text message thing? No? Some people don't have
I
iPhones?
have an Android, so like every time.
He has an
What about the good old fashioned group me thing?
He has an Instagram.
Oh, God. Can we figure out something that everyone has? This is ridiculous. Gavin's on ASD. He should have a Snapchat, right?
Instagram.
How does ASD talk and communicate?
They all have to use numbers.
They're all in one room right now.
Someone text ASD and be like, hey, how do you guys communicate? Do you have a group chat? Do you have a Snap? Do you have a whatever? Figure it out. What? Yeah. Yeah. Perfect.
The squeeze theorem, do we usually use it when there's like a denominator? Because like all the followers use it and have a denominator.
Yeah, well the problem is, why would you even be using the squeeze theorem? Because you tried to plug in and you're having some sort of discontinuity issue, right? So that would make sense if you have a rational function, because the denominator is 0 and it's messing us up, or the denominator is well, I guess you could have an infinity minus infinity. That would be another like indeterminate form that doesn't have a fraction, but most indeterminate forms have like a numerator denominator, so you'd be looking at fractional, like rational functions. Yeah. But there are times, Kevin, when you have like an indeterminate and you'd be looking for creative ways to analyze what's there. But usually we try to get it into a fraction, kind of for the same reason as L'Hopital's. We like 0 over 0, we like infinity over infinity, we like fractions because there are things to do with them. But technically the squeeze theorem doesn't need a fraction. All it needs is someone who's above should have come down the other foot. Someone who's above and someone who's below, and that doesn't have to be just like rational functions that come together or that converge at some sort of point or some sort of limit. So this is one of those weird ones where it's an oscillating wave that's getting shorter and shorter and shorter and shorter and shorter and shorter and shorter, going to zero. But that's another reason why I had to say that the range in part A, which is hidden, is all real numbers because it's continually crossing the axis. Like, well, wait a minute, is the range all real numbers? If it's getting closer and closer and closer to zero, we know that it equals zero, but guys, how high does this function go? Any ideas? We figured out that there's no, like, why is this not working? Okay. Give me a second. It's not letting me scroll up, I apologize. Okay. Is the range all real numbers? Does it go forever high? What do you guys think? I saw the horizontal asymptote, I saw that it was at 0, and I was like, oh, maybe y can't be 0, but then I started considering the function, and I was like, wait, no, y can totally be 0. So y is all real numbers. Was that a valid jump? Yes or no? How high does the function go? So we're thinking about f of x being cosine of x over x, right? Joe, you said yes, the range is all real numbers. How come?
Because when x approaches 0, from to the right, then cosine approaches 1, and x approaches 0, so then it becomes number over 0, which is an infinity.
So Joe's trying to consider what's going on as x approaches 0 of cosine of x over x, in essence, right? Okay. So as x is approaching 0, he thought about, okay, cosine of 0 is 1, 1 over 0 is an infinite. Oh, so what does that mean there exists at x equals 0? Yeah. There's a vertical asymptote of f of x. And if there's a vertical asymptote, that means it's going to go forever high and low? Okay, so if you come from the left, we don't know. Maybe it's only forever high and it's limited and it doesn't go forever low. So we would have to check from below and above. So checking from below, that would be like a negative 0.1. That's a negative, right? But then if I am approaching cosine from below, aren't both of them just going towards a positive 1? The first quadrant and the fourth quadrant in the unit circle are both positive numbers, so right below 0 in the fourth quadrant, right above 0 in the first quadrant. Okay, so this is always positive, but that one will be negative sometimes and positive sometimes. So yes, it will go forever low, it will go forever high, and it will continually, not continually, but it will pass through all those functions to get to that little oscillating wave getting closer and closer and closer to 0. But even though it's getting closer and closer and closer to 0, horizontal asymptote of 0, it's continually hitting, crossing through, which is why we still say range is all real numbers. Good analysis. Good job. Good job, good job. We know it goes forever high, forever low, and it goes through 0. So we're good. Oh man, whatever they're making for lunch, I keep on smelling it. Can you guys? I'm hungry. Okay, any questions on the multiple choice or the FRQs, long answers? No? None? We're good? Or...
There's a brownie though, I'm actually just for the brownie though, not for the just the brownies.
Questions for the homework or what?
Oh, we're just doing for this. Homework? John has homework questions. Let's go, Grace. Homework. That's a perfect transition. Thanks, John. Okay, homework, evens. Here we go. Number 6 and number 8, you can check out the graphs, you can check out the tables, but that should match up with what you thought about the limits.
70.
We were going to infinities because we were doing horizontal asymptotes, right? Yeah. Did you guys get 2 different horizontal asymptotes for number 6? Because you were supposed to positive and negative 2. Positive and negative 2. 16 and 20. Yes, I know. They're double checking graphically and numerically, blah, blah, blah. But number 16, negative infinity. Number 20, negative infinity. Ooh, how'd you guys do with secant? 1 over cosine. It's a basic graph. Ooh. coming from above. Number 30, x equals -1/2 and 3. Those are, I think, the vertical asymptotes. Is that right? But letter B talks about the left-hand limit coming from below, the right-hand limit coming from above. The overall limit would not exist because they don't agree. We okay? Okay, let me give you a second. There's 36, 38, 44, 48, and 70s are coming. Ish. Now, if the right end behavior model matches the left end behavior model, they can just call it the end behavior model if it's true for both sides. But if there are distinctions, if they are different, then you would have to list them separately. You can kind of see that in number 48. Both the right and the left end behavior model agree. So this would be the end behavior model. And then number 70's final answer is ln of 10. Okay, I'm ready for questions. What do we got? 70. Anything else?
Can we just go back to 32 and see it?
Yeah. Oh. Oh, he's got it. He's got it. Sorry, David. All right, I'm going to start with number 70. If you guys have other questions, just let me know. So number, oh, come on, come on. You're right there. You're right there. Show me. Show me. Okay, number 70 says, basically, solve. Find the limit, give a convincing argument that the value is correct. Ooh, convincing argument. This is exciting. So, you guys, some of you just saw what was in the answer key, and some of you understood it, and some of you are still like, yeah, no. Remember how in the summer review packet for AB and BC, there are certain pre-cal skills that I say that might come up randomly? Maybe the double angle of sine formula, maybe the Pythagorean property, maybe something like ln of E is 1, and maybe something like change of base formulas? Well, that's interesting. Do you remember way back when you could change the base of any logarithm? Oh, come on, here, start working. Some days it works and some days it doesn't. It's okay. Take a deep breath. I'm talking to myself, but you can too if you want to. Be like, Jesus, thanks for trying to give me patience. Or at least teach me patience. Oh, now it's not open. Okay, never mind. Oh, now it is open. Well, it didn't take a picture like it was supposed to, but it started writing. We'll take it. So for number 70, there was an old school pre-cal formula that said log base b of x can be changed to any other log base by doing a ratio of the new base to, or of, I should say, x all over the new base of b. So, do we like common logs? No. Do we like natural logs?
No.
Compared to common logs, hopefully the answer is yes. We can take this log and say we want to make you a natural log. And to make you a natural log, we have to do ln of the argument over ln of the old base. Who was the old base? 10. Common log is log base 10. Common log is log base 10. So I can substitute in for him, and then I end up with, an expression, which pretty quickly we could go ahead and say, hey, division by a fraction is multiplication by the reciprocal, so it's going to be ln of 10 all over ln of x. If you want to think about it this way, multiplying top and bottom by the reciprocal. And I end up with, oh hey, the ln's reduced. And the limit of any constant is the constant. What did that all come back to? change the base formula. Change the base formula. We had to think about the logarithms in some sort of common base, and the only way to make it a common base was to change it. So we changed the log base 10 to an ln, or a log base e, by saying, hey, put the x on top and the 10 on bottom. Zoop. Tricky, tricky, tricky. Pre-cal stuff coming back. Anything else in homework you guys want to see? 9? Oh, no, he's not working. Okay, well, that's cool. Let's go find number 9 without zooming out then. Number 9 gives the following directions of find the limit and confirm your answer using the squeeze theorem. And so they give us 1 minus cosine of x all over x squared. Now, I would normally say, like, hey, why aren't you guys thinking your special trig limits? But number 1, they said confirm. Well, wait. Squeeze theorem is just to confirm, right? Oh, which means you should have been able to do it without the squeeze theorem, right? Well, I don't know, maybe not. This looks an awful lot like when we did in our notes, though, doesn't it? If you thought about how cosine of x goes between negative 1 to 1, isn't this numerator kind of bounded? Like, you can only go all the way down to 1 minus negative 1. Oh, I guess that's all the way up. Or all the way down to 1 minus 1. That's one way of thinking about how it's bounded. Because then I could, according to squeeze theorem, go ahead and throw this in between 0, all over x squared is 0, and 2 all over x squared is 2 over x squared. So if I'm considering this guy's limit, what if I take the limit of 0, that's 0. We're going to take the limit of 2 over x squared as I go to infinity. Bottom wins 0 again, true? So what's this guy going to do? Get squeezed in between and have the same limit. The limit is 0. The limit is 0. And then if you guys did want to solve it by hand, I mean, if you realize this guy's bounded, if he's bounded, then the bottom wins. X squared as x goes to infinity versus this guy that won't ever go above 1 or below negative 1. You could have just thought degree test to some degree. And then the other one that I would have used to try to explain it, or I would have tried to use to explain it, would be L'Hopital's, and yet that runs into the exact same problem Joe asked yesterday. With L'Hopital's, we tend to get like a DNE sort of answer, so how does that work? But it's the exact same question that we need to ask ourselves when we get to L'Hopital's about this x to infinity. Whether or not, or how that compares to x to a constant when being applied with L'Hopital's. Anything else?
We did 30.
30. Number 30 is this guy down here, right? He's down somewhere. We're trying to do vertical asymptotes, describe the behavior to the left and right of each vertical asymptote. But left and right, that just means coming in to the left, to the right, from the to the left, to the left. So on the left, so from the left and then from the right, another way of saying that. So first of all, vertical asymptotes, where do we look for them, guys? Denominator, and in the denominator we need to factor to find all the possible zeros. Now a quick word to the wise, a quick reminder. Zeros in the denominator, they can be vertical asymptotes, but what else can they be? Poles. We have to check whether or not the 0 in the denominator makes a 0 in the numerator or makes a constant. If it makes a 0, then we say it's a hole, it's removable. If it doesn't, then we say it's a vertical asymptote. Right? I was going to shorten it, and then it was too late. I was too far in. Okay. Did you guys factor the 2x squared minus 5x minus 3 to be 2x and x? And then we have 3 and 1 and a negative and a positive? Huh? That works too. Just make sure whatever way you use is a way that you will remember without going to your resources. For those of you guys that want to remember the modified x method, you could have multiplied and gotten negative 6x squared. There's your negative 5x. You could get that by negative 6x and 1x. But remember, that just shows me what was there. what was there before it was simplified to be this, you would have had to have rewritten the x term as negative 6x plus 1x minus 3. Group it, a 2x comes out, a 1 comes out. What's in common is an x minus 3. That works. It's not gorgeous, but it works. If you guys didn't know, there is a nifty shortcut to the modified x method that doesn't make any group, where you take the leading coefficient, which is 2, and you write it over both of these. And if you reduce, isn't that going to be 2 and 1? 2x plus 1. And then isn't that going to reduce to 1 and 3? 1x minus 3. It's totally a cheater method though. I mean, it works. It's just kind of tricky.
Does it work?
What?
All of them?
Yep.
Every single one?
Yep.
Such a big brain.
What? Did I steal all your brains with a new factoring
I
way?
use that method.
Here. Do you want me to give you another one?
Something over there. I'm watching the video.
Do you want to try and use it? I'll try and use it. Okay.
Do it again.
Well, let's give you something like, hold on, I have to make up one.
Yeah, squared plus 3.
Yeah, but I forgot it.
You forgot what? This trick?
Whatever Kevin taught me. Which was this trick.
Hold on, give me a second. Okay, what if I give you something like 15x squared? Minus 7x minus I'm just trying to think. It's hard to make these.
It's okay.
Judging for Christine.
I'm fine.
What are you laughing at?
I mean, you can like watch me mouth that word in my head, but yeah, that works. Does it work? I think it works. Now, if you were me, you would have learned the guess and check methods. So you would be filling in your first and your outer and your inner and your last in your head. That's what I would do. But if you're doing the modified x method, what goes into the top? Negative 60. What goes into the bottom? Negative 7. What gets put here and here? And then what's the leading coefficient? Then you reduce. Then you reduce. Oh, this is so funny.
Wait, what's wrong with
So then does it work to have 5x minus 4 and 3x minus 1?
Oh.
Wait, not minus. Sorry, my bad. Plus.
Would it always be the top that
Yeah.
Okay, so it's not 4x.
You like draw a star and then you write above it what the leading coefficient is, and then you reduce, and then the x term is here. And then here's the question.
Was it in
Why
Bible?
was that such a big thing?
Everything is different now.
Yeah, in Bible.
Clear now.
You see clearly now?
When people discovered the wheel has
That the rain is gone. Alright, we weren't supposed to be learning factoring today. Huh?
So it's good.
Any other homework questions?
Factoring.
No other homework questions?
I've already done
Let's do that.
Alright, note section 2.3, continuity. Continuity. Boop. Wait, did we start this yesterday? Oh. Looks like exactly what I did in... Did I steal your... No, there's no way I stole your notes for AB. That's weird. this is weird. This looks, no, we just did like a BC, I don't know. I think AB, I kind of used your notes to do their notes for period 6 yesterday. Something's weird. Huh.
I feel like I've seen these before.
Yes, and you have. But it shouldn't be filled out, which is weird. What? What's going on? Continuity! What are the following 4 illustrations showing? What is the same? Each of these 4 are discontinuous or not continuous at? Where? C. But how? How are they discontinuous? F of C does not exist.
Right.
What about this one? The limit as x approaches C of f of x does not exist. The at doesn't exist. The approach doesn't exist or doesn't agree. The approaches do not agree. What about this one? It completely misses. The limit is infinity, but by definition, if the limit equals infinity, as I come towards a constant, what exists there? A vertical asymptote, which by definition, well, I'd have to, well, not by definition, by the really silly way of remembering a continuous function, in order to get across an asymptote, you're going to have to pick up your pencil and then keep drawing. Remember, the really silly way that you first learned continuity, I think, was whenever you draw a graph, if you have to pick up your pencil. Yeah, I have to pick it up. Yeah, I have to pick it up. Yeah, I have to pick it up. Well, actually, you'll be drawing it forever. But anyway, the limit is infinity. That's a no-go. And I guess they don't agree. The at and the approaches don't agree. But this one, the at and the approaches both exist. But what's wrong?
They drove 1 street down.
They drove 1 street down. Sure. The diner guys are just, a block away. The at and the approaches do not agree. So either the at doesn't exist, the approach or the approaches don't exist, don't agree. Or the approach is infinite, which means, yeah, I'm having issues, or the at and the approaches don't. What am I saying? The definition of continuous. Number 1, the point has to exist. F of C has to exist or has to be defined. Number 2, the limit as x approaches C has to exist or has to be defined. And then, I shouldn't say defined. The limit exists, the point is defined, and the limit has to equal the point. Now for all of that to be true, I decided this year for my poor little AB dudes, just kidding, I don't think they're poor, but they might struggle a little bit. Oh, I don't want any of those, I want gray. That's a struggle. There it is. Boop. I said the at exists. The approaches agree and are not infinity. The approaches agree and are not infinity. And then the at equals the approach. I'll say approaches because we understand approaches. We have to come from either direction, right? Which is why last year we summarized it in this one statement. F of C, the at, has to equal the approach from below and the approach from above. If they all coincide, the function must be continuous. Now guys, what's the one little thing that my little editor, when I was typing and making this line, did not allow me to do that I need to add in? Something's missing. Yeah, I need x to approach C. P.S. Some of you left that out in your forever quizzes. Again and again and again. Now technically, do you necessarily have to remember the 3 conditions separately, or can you remember the statement at the end? Yeah, you can technically just remember the statement at the end. The limit as x approaches C from below equals the limit as x approaches C from above equals f of C. Technically that's sufficient, but just be careful because depending on the piecewise function, they love to give you a piecewise and say make it continuous, and they love to go one step further and say you better know calculus and make it differentiable. Maybe not over and over again, but enough of the time that we at least have to make sure we know how to do it. Some piecewise functions, there is not a unique below and above. Some piecewise functions do not give you a below and above piece. Some of them just give you a not equal to piece. So this might confuse a few of you, depending on. Last year, I think that was for card number 1, 2, 3, 4. I think that was for card number 4. Why am I stating a forever card if you guys already have them written? Because it's a forever card that you need to be responsible for this upcoming test. Boop. Now, hold on, pause. It's all filled out. Why? We did it last year, so write down what you need to remember. Do you remember that holes are removable? Do you remember that holes only have to do with problems with the ats? All of these, if you guys notice, removable are point problems. Do you see it? AKA F of C issues. But what's going on with non-removable? Maybe asymptotes. I mean, that's one. It's asymptotes, or it's oscillations, or it's breaks and jumps. So man, there's nothing in common with all of those. Yes, there is. Removable discontinuities is a point problem. If you can redefine the point, you can quickly fill the hole. If you can make a piecewise function and just make a point, if you can reassign the value of that point that is removed and get it to fill in, you can fix that issue. Or if you have an algebraic function that you can simplify away and factor it away. Point problems are removable, but how can I describe non-removable? So think about your definition of continuous. Either we're talking about F of C, the points, the ats, or we're talking about the limits. It's a limit problem. Do you have limit issues? Well, it's a lot bigger than a point issue. Point issues are removable. Limit issues, well, can't just assign a point. Oh, we have one more minute. Just kidding. 20 seconds. Student council kids, you can start packing up. You know what to do. Go videos online, and I think we have a homework due. Not right after the break. Not on Tuesday. It's on Wednesday. Spoiled rotten. But if I were you, I'd get it done. Oh, by the way, what is due after the weekend, though? Correction. Don't you have a summer review quiz and a polar parametric that you're supposed to be figuring out what went wrong? Yeah. So those of you guys that have not got them back yet, here they come.
I got 8 out of 10.
Anybody of the student council? Persuasion?
Sorry.
No? Okay, you guys got it. Bye, guys. David, come on down. Abby, you're right here. Janelle, come on down. Lainey, come on down. All the people that weren't on 0 for you on Wednesday. Diary. There are correction papers in the back. Ooh. David. David Park. Janelle, come back down. Abby. Kyrie.
Hey.
Lainey. Gavin. Oh, Gavin. He's in AB.
Yes, this is the summer review.
Okay, let's go back and get correction papers really quickly and make sure David knows where to get them to.
One for each or one for both?
Get one for the summer review. Polar parametric you can correct on it because I think there's room. The summer review though, it's too packed. There's not enough space. If anybody else needs extra correction papers, they are on the backboard. For the rest of you guys, ready, set, let's explore. Ready, set, let's explore. Something that I appreciate in this book.
I have correction
Save it for a rainy day.
I'll give it to Ryan. Ryan, I got you.
Are you stalking
Wait, why are we exploring? Explore. Only like 3 of you were supposed to be there. Exploration. Good. Removing a discontinuity. Finding a continuous extension. Ooh, new vocab. We had a right and left end behavior model in section 2.2. We had the epsilon delta proof in section 2.1. Now we have a continuous extension in 2.3. Oh, it's new vocab. They're saying you zoom in tables, but maybe you guys can consider this function, even though it's nasty and kind of gross. Now, if you like using your calculator, maybe you'll just go there. But if you don't, or you're being lazy, and you have some mental math skills, maybe you can consider what this function looks like without using a grapher. What do you have so far? Factoring denominator, that's easy. What's my domain? Yeah, x can't equal plus or minus 3. So what's going on in number 2 around x equals 3 and x equals negative? Oh, just positive 3? Just positive 3. What's going on around positive 3? Did you guys plug it in? We know the function doesn't exist at either one, but how does it not exist? This one I have 27 minus 21 minus 6. Isn't that a 0 over 0? Yeah. Which technically 0 over 0 does not exist, which is why with limits we can't say the limit equals 0 over 0, because no, you're supposed to keep going and maybe it equals a constant. But we can say, oh, yep, the function does not exist, 0 over 0. But what's different with negative 3? Negative 27 plus 21 minus 6. It's a number over 0. So why are they just having me look at positive 3 and not negative 3? Because it's called removing a discontinuity, so they're only having us look at the whole. So what's going on around x equals 3? Everything's great, everything's fine, everything's peachy, all the limits are existing and the points are existing and the function is continuous, aka what's going on? We have a whole at 3. That's the only place we have an issue. It's not going to infinity, it's not broken. Everything's fine. You can say the limit exists, etc. How should f be defined at x equals 3 to remove the discontinuity? AKA, there is a hole, how would you fill it? Well, you wouldn't fill it here, or here, or here, or here, or here to make it continuous. You have to fill it only where the function is missing its point. So how do we find that, guys? Simplify. Okay, sweet. Let's factor the cubic polynomial. They're so cute. They're How do we get rid of, who wants to factor? Nobody. So why don't we just do a quick little long division? We can't do a synthetic division. Well, I guess we can. X squared minus 9. What do we get? X. And then we end up with x cubed. Those will cancel. Minus 9x. Ooh, negative 9x. We're going to have an x minus 9. Is that a thing? So x squared minus, oh, that's a squared, sorry. X cubed minus 9x, oh, never mind. The 9 goes down here by the 7. It's really hard to do long division when you have like a line. That's a circle. Has anybody finished their long division? I'll do long division as you guys go ahead and leave. That's fine. Happy Spirit Day. Happy 3.5 day weekend. What?
Are you our teacher's sponsor?
Yeah.
20 minutes.
Me and Mr. Stripe.
Well, I thought that maybe
Mr. Stripe and I.
you don't look like that.
Oh, the business office. I don't.
No, I'm just saying. No, because
And Kevin, maybe you can think about as you do your table, you could have done fewer values and still figured it out. Does that make sense? Morning.
I did that last year.
Is that what it's always called?
The formula's on Fridays.
And I got my teacher.
Yeah, most of
You want me to come with you?